Hope everybody's having a good day. We're going to run through a few more examples of rational functions and their graphs. And this is going to be to finish off section 2.7. All right, so this first one I'm going to start everybody off with y equals x squared minus x minus 6 divided by x squared minus 9. All right, and I'm just running down the steps that you have attached to your help sheet. So step one is factor, cancel, check for holes. So for us, we have to factor. In the numerator, we have a trinomial. So trinomials factor into two binomials. In this case, what numbers multiply to get negative 6 and add to get negative 1. In the denominator, it's difference of squares. So we have to take the square root of the first term, square root of the second term, put a plus in one, minus in the other. So we factored. Does anything cancel top and bottom? Yes. The x minus 3. So what we're going to be left with is x plus 2 over x plus 3. All right, and whenever we have a canceled factor, we're going to end up with a hole. And the hole always occurs where the canceled factor would be equal to 0. In other words, if you move negative 3 to the other side, the canceled factor is going to occur at x equals 3. So, 1, 2, 3. So the hole is going to occur at 3. Okay? Number 2, zeros occur anywhere the numerator is equal to 0. So the only numerator we're left with is x plus 2. So we set x plus 2 equal to 0 and solve. And so our 0 is going to occur at negative 2. So at negative 2 on the x-axis, give yourself a point. Next, the vertical asymptote occurs anywhere the denominator is equal to 0. So the only thing we have left in the denominator is x plus 3. And so when you solve, you get minus 3. So we'll have a vertical asymptote at negative 3. So sketch that in as a broken line to help us with the graph. Next up, number 4, y-intercept. Y-intercept occurs wherever the original function is equal to, when the original function is evaluated at 0. So what we do is we replace x with 0. So we'd have 0 squared minus 0 minus 6 divided by 0 squared minus 9. So when you do all that simplifying, you get negative 6 over negative 9, which is positive 2/3. So if that tick mark is 1, 2/3 would be right about there. Okay? And then finally, number 5, the other asymptote. We have to check what are called the degrees, the biggest powers. And I'm going to choose my highlighter here because I just need to highlight. It doesn't matter if you start with the original terms that have the biggest powers or after you've done the canceling. Doesn't matter, you get the same results. If you start off with the original, the biggest power up top is 2, biggest power down below is 2, and the numbers in front of each of those are 1s. So the horizontal asymptote then that we would get would be at y equals 1 over 1, which is 1. And if you'd rather wait till you've factored and canceled, the same idea. Now the term with the biggest power up top is x, and the number in front is 1. In the bottom, the term with the biggest power is x, number in front is 1. So either way, you get 1 over 1. So our horizontal asymptote is through y equals 1. All right, number 6, we don't have to worry about any volcanoes because we don't have even powers in the denominator. So we just have to decide on end behavior, right? And end behavior, we're deciding whether we should be on the top side or the bottom side. Right? So should we be on the top side of the asymptote or the bottom side? And the answer is we have to be on the top because if we were on the bottom, as we traveled left to right, we'd have to go down before we got to the vertical asymptote, and we can't go down because there's no 0 left of negative 3. So we can't do that. So if we can't be on the bottom, we have to be on the top side. So we'll start on the top side of the horizontal asymptote, and as we travel to the right, we can't cross the vertical asymptote, so we have to go up. Without any volcanoes, we have to change direction, so we have to be going down on the other side. And then we're able to pass through the 0 the y-intercept and get closer and closer and closer to the horizontal asymptote, this time from below. And all we need to remember, there's one last thing. We need to make sure that, oops, sorry, hit the wrong button there. There we go. We just need to remember that we have a hole at 3. So I left a little space there so it was easy for me to put in an open circle at 3. Okay, so there's a pretty good depiction of the graph of this rational function. All right, feel free to pause the video if you want to get this one into your notebook. Okay? All right. Next example. Next one. Here's the next function. Negative 2 over x plus 2 squared. Right? And we're going to try to get a decent picture for the graph of that function. Okay? All right, right off the bat, number 1, factor, cancel holes. Well, there's nothing you can factor in the top, and the denominator is already factored for us, so you can see nothing cancels, so there can't be any holes. All right, so I'll just be real specific there. No holes. Right? Next, we have zeros anywhere the numerator is equal to 0, so we set the numerator, negative 2, equal to 0 and solve for x. Obviously, there is no x there to solve for, so we don't have any 0. Okay, we'll have a vertical asymptote anywhere the denominator is equal to 0. So we set the denominator equal to 0 and solve. Get rid of a power of 2 by taking the square root. So we get x plus 2 equals plus or minus 0, but of course plus 0 and negative 0 are the same thing. So all we have to do is move plus 2 to the other side by subtraction, and we'll get a vertical asymptote at negative 2. Now I hope you remember from last week that when we have an even power, let me choose my highlighter tool here, when we have an even power in the denominator, that means we're going to have a volcano. So that means when we are sketching in our curve, we don't change directions on either side. Okay, so just keep that in mind. Number 4, the y-intercept will occur wherever the function's evaluated at 0. So here we have to evaluate m of 0, so that's going to be negative 2 over 0 plus 2 squared. 0 plus 2 is 2, 2 squared is 4, and negative 2 over 4 reduced is negative 1/2. So if this tick mark is negative 1, negative 1/2 is going to be located right about there. Okay? Step 5, our other asymptote. Check the powers. The biggest power up top, meaning in the original function, the biggest power on a variable up top is 0. And if you multiplied out the denominator, the biggest power down below would be 2. So if the top has a degree of 0, and the bottom has a degree of 2, that means we're on letter A. The degree of the top is smaller than the degree of the bottom, so we're going to have a horizontal asymptote at y equals 0, which is the same thing as the x-axis. So the x-axis will be the horizontal asymptote. Remember, that just tells you what happens at the end behavior, right? And then we finish off with the end behavior, all right? And with the volcano that we've already talked about, we know we're not going to change direction on either side of the vertical asymptotes. We have to keep that in mind. But we still have to decide for ourselves whether we should be on the top side or on the bottom side of the vertical asymptote. And I would agree this time there's not very much information that shows you that. So when you don't have much information, you pick a value for x left of the asymptote. So since the asymptote is at negative 2, you pick something like negative 4 or negative 5 to see whether you should be above or below. So if I choose negative 5 as an example, the function evaluated at negative 5 would be negative 2 over negative 5 plus 2 squared. Negative 5 plus 2 is negative 3, and negative 3 squared is 9. And the important part is that that number is negative. So when we go 5 to the left, we have to be below the x-axis. So we can't be above, we have to be below the x-axis, the horizontal asymptote. And then that just gets everything going, so now we can have this first part of the graph that starts below the x-axis and goes down at the vertical asymptote. And because we have that volcano, we don't change direction, so we're going down on the other side, and then that allows us to pass through the y-axis at -1/2 and move towards the horizontal asymptote. Okay, so we end up with an upside down volcano. All right. Hope everybody's doing okay on that one. Feel free to pause the video if you need to jot down a few extra things. Otherwise, I'm just going to move on to the next example. The next one, let's see, did that one. Okay, the next one I'm going to do 3x squared plus 1 over x. And we're going to get a decent graph for this function. All right, so we'll get started right off the bat. Number 1, factor, cancel, and wholes. You can tell quickly that nothing factors in either the denominator or the numerator. So no wholes to worry about. So again, just be real specific there. No wholes. Number 2, we're going to have zeros anywhere the numerator is equal to 0. So we set the numerator equal to 0 and solve. And you can see quickly we run into problems because we have a negative number on the other side. When we take square roots, we're going to get an I involved. So this negative is going to come out as an I, which means we're not going to have any zeros. All right? Number 3, the vertical asymptote occurs anywhere the denominator is equal to 0. So you just set the denominator equal to 0, and you can tell right away we'll have a vertical asymptote at x equals 0, which of course is just the same as the y-axis. Because of that, because the asymptote is on the y-axis, when you try to find the y-intercept, you see that you run into issues. When you try to evaluate the function at 0, 3 times 0 squared plus 1 over 0, we get an undefined fraction. So therefore, the curve doesn't pass through the y-axis. And then finally, the other asymptote we get by checking the degrees. The biggest power up top is 2. The biggest power down below is 1. And when the degree of the top is bigger than the degree of the bottom, then we're going to end up with either an oblique or a curvilinear asymptote. In this case, it's going to be oblique. I'll show you why in just a second. And to figure out actually what it is, we have to scooch over to the side, and we have to do a division problem. We have to take the numerator and divide by the denominator. Notice I had to put in a missing term into the numerator. I had to put in a 0x to the first. Now we start doing our division like we always do. X times what is 3x squared? Answer, 3x. Anytime something goes into the answer, multiply. 3x times x is 3x squared. Draw a line across and subtract. Scooch down the next term. Start the whole thing all over again. X times what is 0x? Obviously 0. So 0 times x is 0x. When you subtract, you get 0. And when you drop down the next one, it doesn't make sense anymore. X times what is 1? Of course, that doesn't work. So the 1 is a remainder. So when we do our division, what we get as a result is 3x plus 0 plus 1 over x. And if I just skip the 0, you don't have to worry about that. And then we pitch the remainder into the garbage. The asymptote then is going to be y is equal to 3x. And feel free to pause the video anytime you want. I'm going to move back to my picture. and sketch in y equals 3x, which is just a straight line that goes through the origin and has a slope of 3, so up 3 over 1. And so it would look something like that. Right? And finally, number 6, we have to worry about end behavior. So do we have to start on the top side or the bottom side of that asymptote? Well, let me start with the one that's wrong. If I started on the top side, as I move left to right, my only choice would be, as I approach this vertical asymptote, would be to go up. And I'm not allowed to go up because I don't have a 0 on the left side, on the negative side of the x-axis. So I can't do that. So if I can't be on that side, so if I can't be on the top, I've got to be on the bottom side. So as I travel left to right, I'm still not allowed to cross the vertical asymptote, but now I can hang a U-turn and go back down. Without a volcano, I have to change direction, so my curve has to be going up on the other side of the vertical asymptote. And once again, I can essentially U-turn this thing and approach the oblique asymptote. Okay, and there's a pretty good representation for the curve of this rational function. All right? Feel free to punch this one out on your calculator, but you might have to mess around with the window a little bit, especially up and down, to get a decent picture of it. Okay? And to finish off, I have one last example. And the last example I have here I called P, and the function is negative x squared plus 3x plus 2 on top of x plus 1. Okay, and we're going to try our best to get a decent graph for this function. Okay, so step number 1 is to factor, cancel, and check for holes. So, like always, we do that. We just give it our best shot. The denominator does not factor. It's just a plain old binomial. The top's a little bit tricky for me because of that darn negative, so I'm going to give it a try. What first could I multiply together to get negative x squared? I'll try negative x and positive x. What lasts could I multiply together to get 2? Well, obviously I could try 1 and 2 or negative 1 and negative 2. Not sure either one of those is going to work, though. Let's see. I don't think so, right? Because if I try negative 2 and negative 1, the outsides and the insides would not work out. If I switch that around, if I tried negative 1 here and negative 2 there, that still doesn't work. So this one must not be factorable. And if it's not factorable, then we can't cancel, and therefore we don't have any holes. Okay? Next up, we look for zeros, and zeros of course occur anywhere the numerator is equal to 0. So we could set the numerator equal to 0 and solve. But we just showed that we can't factor. So if I can't factor this, I would then need to go to quadratic formula. So I'd have to then apply quadratic formula to find the zeros. So x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And let's see what we get here. Inside the square root, we'd have 3 squared, so that's 9. Negative 4 times negative 1 times 2, so that's positive 8. And down below, we have 2 times negative 1. 9 plus 8 is 17. The square root of 17 is going to be about 4 point something. Just going to need to dig out a calculator. The square root of 17 is about 4.1. So when I do the adding and subtracting on the top, negative 3 plus 4.1 divided by negative 2 is negative 0.55. And when I do the subtraction, negative 3 minus 4.1 divided by negative 2 is 3.55. Okay, so we'll have a 0 at negative 0.55. So if this is negative 1, negative 0.55 is about there. And 3.55, so 1, 2, 3, 4. So 3.55 is right about there. Okay, vertical asymptote is going to occur anywhere the denominator is equal to 0. So we set the denominator equal to 0 and solve. So we have a vertical asymptote at negative 1. Okay, I'm going to have to scooch this over a titch. Next up, our y-intercept is going to occur at the function evaluated at 0. So everywhere you see an x, put in 0. So negative 0 squared plus 3 times 0 plus 2 over 0 plus 1. So we end up with 2 over 1, which is 2. So it's going to hit the y-axis at 2. All right, and finally we're looking for that other asymptote. And once again, we have to check the degrees. We have to check the degrees. The biggest power up top was a 2, and the biggest power down below was a 1. And whenever the degree of the top is bigger than the degree of the bottom, we're going to have an oblique or curvilinear asymptote, and we'll have an oblique one this time. And we get that, find that, by doing division. So again, I have to scooch over to the side and do a division problem, taking the numerator and dividing by the denominator. So here we go. X times what gets you to negative x squared? Answer, negative x. Anytime something goes into your answer multiplied, negative x times x times 1. Draw a line across and subtract. So we end up with 4x, drop down the next term, start it all over again. X times what is 4x? 4. Anytime something goes into your answer multiply, 4 times x and 4 times 1. Subtract. So we end up with a remainder of negative 2. Please remember the remainders get tossed in the garbage, and so our original function now has become negative x plus 4, and that then becomes our oblique asymptote. So I'm just scooching this over there so you can see it a little better, and then back to my graph, and I need to draw an oblique asymptote, negative x plus 4, so that means it would go through the x-axis at 4 and have a slope of negative 1. So I'm going to be really careful and draw it as carefully as I can. So that means it would actually go down 4 over 4. Let's try that again. I'm trying to use my ruler. To get a decent line in there. Okay, so there's the oblique asymptote. And then to finish off, like always, we have to decide whether it should be on the top side or bottom side of that asymptote. Okay, and I won't waste your time on this example. We have to be on the top side so that as I travel left to right, I'm just going to hang a left and go up. And then without a volcano, I have to change direction. So on the other side of the vertical asymptote, I have to be going down. And then just look ahead. Can you pass through the x-axis once, the y-axis, and the x-axis a second time? Yep, doesn't look too bad. We're going to come up, go through the x-axis, through the y-axis, make a turn, go through the x-axis again, and then we'll be approaching the oblique asymptote. Okay, and once again, pretty decent graph for that rational function. All right, that's the last example I'm going to do with everybody. So please continue to work on these. Tomorrow in class, we'll go through as many as we have time for, turn this one in, and then get ourselves started on section 8. All right, hope everyone has a good day, and we'll hope to see you tomorrow. Bye.